Hello, it's Keith here, and this is lesson 18 of the multi-platform series of my Z80 assembly programming tutorials. And today we're looking at the optimization of a program, in this case a speech synthesizer. Now, you may have seen last time's episode, we looked at the disassembly of a speech synthesizer. And doing that, this is obviously software I didn't write, that's why I'm disassembling it. But looking at that, I saw a lot of things that were easily improvable. And that's why I was a bit surprised when I saw that it was originally a type-in, because there's a lot of code here that could very easily be reduced in length. And that means people typing in things they didn't need to. Now, the optimizations we're going to look at, it's really some of it's general advice, and others of it is, you would need to look for similar things in your own code and work out what's appropriate there. But basically, optimization tends to split into sort of three kinds of category. There's the kind of optimization that's really worth doing as you're coding along. Just use the quicker version. It's quicker, it's shorter, it uses less memory, it's faster. No reason not to do it. Then there's the ones that are a little bit tricky and maybe you want to leave a little bit later, but they're still worth doing. They improve things, but they make the code a little bit more complicated. And if you're merging two subroutines together, for example, and then you remove one of the subroutines altogether, then the optimization was a waste of time, and you might end up with optimizations that really don't make any sense anymore if your code is still changing. And then you have this sort of final kinds of optimization, which are going to take a lot of time, are very complicated, and are the kind of things you probably only want to do once the program is basically finished and you're happy with it. Because, as I say, you can't properly optimize things until you know exactly what your program's going to do. And if you're still writing it and changing it and improving it, you won't know what your program's finally going to do yet. So I say that I would think of them as splitting into three cases. We're looking at this speech synthesizer today, but I think the stuff I'm going to be discussing is worth you knowing for any kind of project. Now, with regards to the speech synthesizer, I disassembled this. It was an old program that simultaneously appeared in an old Amstrad Action and also as a type-in a French magazine. I didn't write it. I'm giving you the source code for my modified version. You're welcome to use it in any way you feel appropriate. However, I cannot say that it's my work because it's a derivative of copyrighted work. So use it at your own risk and make the judgment of whether you think someone from the 80s is going to come and sue you if you use it in your own little game. Up to you. I just can't give the same assurances I usually do because it's not my code. Anyway, first of all, let's go over to the source and let's try it out so you see what we're actually working with today. So this is the file, this is speech final, this is the final optimized version. So if I just assemble this here. Okay, it's just assembling now. Okay, and then if I do, what's the address we have to call? I'm losing track, I think it's 100 now. That's one of the things, the original one loaded to a very specific memory address, but now because we've got the source code, we can... Okay, that's quite enough for that. So this version has been coded to say, I am a CPC, you are a worm, you will bow to my Z80 superiority. So the computer is quite smug in its speech synthesis capabilities. Anyway, obviously you can put any text you want in here, it will say it, and you can see I've actually modified this code to work on a variety of different Z80 systems, and I'm actually now ported it to the 6502 as well, and I'm going to port it to the 68000 because why not? That's the reason I disassembled it, so we have something we can modify. Anyway, we're not going to look at this source code here for the actual changes because it's going to be better if we look at these examples on screen here because I've taken various screenshots, and these will more clearly show what has been changed. We're going to discuss each kind of optimization, and as I say, the so-called easy wins, these are the easiest things. I'd suggest you do these as you're writing your program. Okay, so let's take a look at them. Right, so the first one here is in the code we saw a very large number of cases where there was jumps using JP to memory destinations to labels that were very close to the address. Now, JP uses 1 byte for the JP command, 2 bytes for the address, and so that's a 3-byte command. Alternatively, though, we can use JR. Now, this stores a relative offset, and this only uses 2 bytes, 1 byte for the JR command and 1 byte for the offset. So if the destination is nearby, we're saving a byte every time, and it's going to be generally faster. So that's one thing to bear in mind. In some cases, we have to trade memory for speed. We can unwrap a loop, and that makes our code faster but bigger. But if we make our code shorter and do the same thing, the sheer number of bytes the Z80 is having to load in for the program code becomes shorter, and so we actually save memory and speed at the same time. And so an unconditional JR I think is always faster than a JP. Conditional, it's debatable, but unconditional I think is always faster. So anytime you see a JP you can change to a JR, go ahead. You might not want to do that in the very, very earliest case. If you're still moving your code around, you don't want to have to keep switching between JPs and JRs, but there's no disadvantage to a JR in your code, so just go ahead and use them. Now, to be fair to the code, they didn't have, but are ones that it's definitely worth you remembering. If you want to load the accumulator with the value 0, that's a 2-byte command, one for the LDA and one for the 0. The command XOR A, though, is a 1-byte command, so 1 byte less, so half the length, and XORing any value with itself ends up with 0. So XOR A loads the accumulator with 0, and it saves a byte. In the same way, if we want to compare the accumulator to 0, well, we just need the 0 flag set, and we can do that simply by doing the OR A. That will effectively do a compare to 0. That's a 2-byte command, that's a 1-byte command, 1 byte saving, and as I say, I would just always do those. Never, unless you're an absolute beginner and you really need the clarity, never use LDA, 0, just use XOR A. Never use CP0, just use OR A. So that's something to bear in mind. Now, another really common one in this code that was really quite surprising when you consider that this was supposedly a type-in. I say supposedly because the Amstrad Action Word version, which was on a disk, came first, and the type-in came later, and I suspect the type-in was copied from the commercial program. So I don't believe this was originally a type-in. Anyway, there were a large number of cases where you saw a call to a subroutine followed by a return. Now, if you're just writing your program and quickly knocking something together, that's fine. However, a call coming back and then being hit by immediate return, this is, firstly, you've got an extra byte command here, but also you're using the stack, and that's going to be slow because when you call, the return address is pushed onto the stack, and when you return, the return address is popped off. Now, if we replace this call to this subroutine and this return with a simple jump to the subroutine, there is no difference in the resulting function of the code program. The only difference is we weren't pushing things onto that stack for no reason. So again, this is a really easy win. There's no disadvantage to doing this, and it's not even like the jump relative that there's the differences in the distance you're jumping to. It's simply, you know, there's no point returning immediately after a call. Just do a jump to the subroutine you want to call. So that's an easy win, so to speak. This is another one that's definitely worth you bearing in mind. Now, sometimes you'll see a call to a subroutine and then a return or a jump to a subroutine, and then you'll actually look at the subroutine, and the subroutine's sitting on its own with nothing before it that does anything important to the subroutine. Now, what you can do is you can move that subroutine in the code to be immediately before that call to the subroutine or that jump, and then just let execution flow in. So before we were loading the accumulator with 3, and then we were loading HL with this address here, and then we're calling play wave HLA times. Now, we could have changed that to a jump, as I said before. That call and that return could have been replaced with a nice jump. But instead, what I've done is I've simply moved the play wave HLA times subroutine to immediately after this, and then I've taken the call out altogether. And so execution effectively flows into this subroutine now, and we've saved all of those bytes there, and it's going to be faster. The only tricky thing with this is I often will rem out the original call or the jump so that I can see it's still there, so I don't get confused and think that I can just put some code before this subroutine so that I remember that the execution needs to flow into the subroutine. You could catch yourself out, but again, there's no reason not to do that really. So that's another one that's worth doing. Now, this was a really weird one. In the code, there's various places where an XOR A followed by add with carry were being performed. Now, it's common to see this with subtract with carry because the Z80 has no subtract without carry. So the only way you can do it is you can clear the carry, which is what XOR A is doing there, and then you would use add with carry. But the Z80 does have an add command that's 16-bit, and I don't know any difference between the two that is going to affect this code. So I just changed the add with carry to an add, and now we've saved the XOR A byte there. As I say, I don't understand why they did that. It could be force of habit of the programmer. Maybe they always use the subtract with carry and they simply forgot. Very easy, totally forgivable. But as I say, we can optimize and save a byte there. So that's what I've done. Now here's another one that I would definitely suggest you do. I was looking around the code. This isn't a first case one because you need to have your code pretty much finished here before you can identify this. But I noticed there was an awful lot of times when this play wave routine was being called with the accumulator loaded with a value of 5. So, well, there's a simple way of working around this, and I haven't actually taken the screenshot here, which is a bit sloppy, but all you do is you load the accumulator, you create a subroutine that loads the accumulator with 5, and then flows into the actual routine that you were going to run. And then basically every time you do this, rather than loading the accumulator with the value and then calling the subroutine, you simply call the subroutine that will load the accumulator with the value. Now, basically, you're saving 2 bytes every time this subroutine is used. So this can become very, very effective. You know, if you're running this 100 times and you've moved the loading of the accumulator so that it only needs to occur once, here it is, it's up here. So you're effectively saving 200 bytes there. In the original version of the code, I actually had lots and lots of these. So I had ones that would load the accumulator with 1, 2, 3, 4, 5. I had to have jumps that would jump to the subroutine. Obviously, you can't have lots of different versions here that just flow in. So I had the jumps, but it was still worth it because, as I say, the original code has dozens and dozens of these, all using the same accumulator values. Definitely worth considering. Now, another one that's an easy win here. So here they're loading the accumulator with the equivalent value of 13. OD is 13 carriage return. And then they're loading that into the HL. But the code didn't actually need the accumulator to contain that value in any other place. Now, the HL register pair is special. We can actually load any value we want here. And so by changing this to a direct load of the value into HL, the HL memory address here, we're effectively saving a single byte from the LDA part of that command. Now, if the accumulator needed that value for something else, that wouldn't work. And it wouldn't work if we were using BC or a different register. But in this case, easy win. I would often miss that, to be honest, in my early stages as well. But as I say, you can do that. It's definitely worth doing. On the same kind of thing here, I looked at the code here and I noticed, well, they're doing something similar here using the BC pair here for the string address of the processed text data that was to be spoken. And they're loading the value space effectively into the BC register here in a similar way as before. Well, in this case, I realized the HL pair was free, so we'll use the HL pair and then we can put that in line again and we can again save a single byte there. If HL free, HL is the most powerful, the most capable addressing command for working with destinations and things. So if it's free, you should use it for that kind of thing. IX can do a lot too, and IY, but they use more bytes in their commands because they're designed to work with offsets. So if you're desperate and if it saves you other code, it's worth doing, but HL is the most memory efficient. Okay. Now, there's a bit of text here which we'll read out because it's important. When optimizing your code, test often and backup too. Definitely. It's bad enough when you're coding your program, but you can ruin your program while you're doing this kind of optimization. And if you make 200 changes, you haven't compiled, and then you compile and the program crashes, well, you're probably going to have to check all those 200 changes. And if you forgot to save a backup before you made those 200 changes, you will be crying for the rest of the day. So enjoy that. So yeah, back up your code and test as often as you can. I was making just 1 or 2 changes each time and then running the test again. That may not even be enough, because in the case of a speech program, you might find, depending on the speech you're saying, it seems to work fine. You change the speech. Oh dear, now I've put a full stop at the end. The code that changes the pitch at the end of the sentence isn't working right. And that's why you need your backups as well, because, as I say, just because you're testing, it doesn't mean you're testing every single possible permutation and combination of your code, obviously. So, the backups are there to help you figure out what's gone wrong if your short testing wasn't enough. But with modern tools, if you've got your environment set up quickly, like I use WinApe for most things, or I use the master system for my Z80 development if I'm not using WinApe. The reason is it's got no operating system. It starts up instantaneously, so I can test and test and test very, very quickly, and that means I can test basically every few lines I write, and that means I don't spend time working out which one of the 20 changes I made, and may not even be an intentional change that has caused the bug. You might accidentally knock a key on your keyboard and not realize you've done it and remove a line of code. And those are the kind of bugs will cause you hell. And if you can't remember if you can't use the undo buffer to check what's changed recently, you might be stuck there finding that for half a day. So as I say, that's definitely worth doing. So anyway, those are the relatively easy wins that you can maybe make while you're writing your program. We're now going to discuss some other ones that I found that are harder to do, and you would need to be closer to the end of your project before you could make them. Okay, so the first of these was regarding the initialization code with regards to processing the strings. There was a variety of subroutines that were being called that were doing jobs, and some of them, I mean, I would always keep something separate in a subroutine if it's very big and very complicated, even if it's only used once. But a very short subroutine that's literally only being used once, it really doesn't make sense to have that as a subroutine. So in the case of this subroutine here, well, it was pretty much just this piece of code here. So all I've done is I've moved it in line and removed the subroutine. I had to change the condition here because of the way the code works slightly different. That was some more optimization as well. Save some memory. No negatives. Again, that you might not want to do that in your early stages because you might have that as a subroutine because you're planning to use it a dozen times. But you might find later on you actually only used it once, and so again, that's the kind of optimization you do. Here's another curious one. So here they're loading the HL with the address of text raw string. And then they're loading that into raw string pos. No reason they needed to use HL for that. And then they're loading HL with 0 and they're writing it to these two addresses here. Well, that's fine. But then later on we notice they're loading D with 0 as well. Now, actually, I managed to get rid of that loading of D with 0 because that wasn't needed as well. But hypothetically, if that was still needed, well, why are we using HL for this? We could have just used DE for that, and then D would be set to 0 as well. So that's what we've done here. Also, in the case of this kind of thing, again, handy to have HL free at all times. And you can see actually I've actually used HL for something else as well. So basically, by using DE, I've got HL loaded with the address of the translated string. So I've actually gained some functionality there as well by freeing up HL. So as I say, definitely worth doing. Now here's an interesting one. So I mentioned before about the code has some functions to change the pitch depending on if the end of the sentence is a question mark or full stop, changing the pitch up for a question mark or down for a full stop. This code works on two phonetics, and one of the phonetics it will increase or decrease by a value of 1, and the other one it will increase or decrease the value by 2, the value being the speed and effectively the pitch. So these pieces of code are basically identical. It's just a value. It's just either working with a value of 1 or a value of 2. And so all I've done, looking at the code, the finished version of the code, I could see there was a register free. The C register wasn't being used. So all I did is I changed this pitch code. And so instead of using a value via incs and decs of the accumulator, I'm simply adding C or subtracting C. And then this piece of code here now can do the job of all of this code because the C register is now the part that decides how much is going to be incremented or decremented. It saves a lot of code. As I say, that's the kind of thing you might want to leave till much later because maybe you need that C register for something else, and maybe you haven't figured out how you're going to change the pitch, so it might not be appropriate to use the same piece of code for both. Now, in the same kind of way of looking at things, there's actually multiple speech playback routines. They're basically little wave files, little binary wave data. Now, originally there were 2, but I added a third, and we'll discuss why I added a third later on. But looking at them, they were almost identical, and with a bit of, again, tweaking and using the registers in different ways and things, I noticed that the initialization routines were identical, and most of the main playing routine was also identical. And so I changed these, and I broke out the initialization routine into a subroutine called sound init, and the play routine into a routine called sound play sample. And so this means that all of this code that used to be doubled in the original version is now used only once. And as I say, I added a third routine because I managed to save some byte data for the wave samples. So that's one we'll discuss in a moment. Okay, so there we go. Now, again, in the same way as before, we had various code that did the same thing here. A lot of routines here that would load the accumulator into switch toggle, pop AF and return, here again, and here again, all 3 times with the same ending sequence. Now, that load of the accumulator into an addressor, that's 3 bytes. Pop AF is 1 byte and the return is 1 byte. So this is 369 bytes. Well, I've just got that a single time. I'm using jump relatives to jump to that, so I'm saving a couple of bytes there. So again, no reason not to do that if your code is finished and you know you're not going to mess around with the end of that routine later on. Now this is interesting because I actually changed this again. This isn't the final version of the code. I found another optimization while I was doing the 6502 version. But here, at the start of this routine here, the wave loop count was being loaded from the accumulator into a memory address, and the 4-bit wave was being loaded in from HL. Now this was being done as part of the initialization, but I actually broke this out. And so in this version, you can see here, I'm backing up using the accumulator here, and this is so that this routine here doesn't have to do this. So basically we got rid of this altogether, I think, in the end. And so I took these out, and then I'm just using them, I'm just keeping them in the accumulator and HL, and this makes the code a bit shorter, and I actually freed up one of the variables as well. Okay, so as I said before, I actually added a sample playback routine, the reason for this is when I broke down the code and worked out what samples were being played for which kind of phonetics, I noticed there was some serious discrepancies. Well, firstly, there was data that wasn't used by any phonetic. There was a huge block of data like this. Nothing used it, so I simply took it out. Some of the blocks were actually weird lengths. Some of them were a couple of bytes too long, and so I remmed out the bytes that weren't needed. One was actually too short. If the sequence was too short, it would actually end up playing the byte from the next routine. I don't know if that was accidental or intentional. I actually used that intentionally. I reorganized the wave samples, and so that in a couple of cases I was able to rem out a couple of bytes that were needed because the couple of bytes from the next sample were the same, and so just let the playback flow into what is technically the next sample. So optimizing the data, checking all the data is really needed. That saved quite a bit there. The real saving, though, there were two samples. One was the silence sample and one was the T sound, and these used a single byte repeated 63 times. Well, that's just crazy talk there. So all I did is I created a new wave playback routine. Now that I had my shared sound in it and my shared sound played sample routine, all I needed to do was have this routine here, and I could reduce those from 63 bytes to effectively 0 because I simply used the wave sample data of another sample, because all I need is something that has an 88 value and something that has a 0 value, and I can find those easily within other samples. So that was a huge saving. So even though this code is using quite a few bytes, it's not using 126. So massive saving there, definitely worth doing. This is another very, very interesting one. I actually found what I think is a bug in the code. Now there's a lookup table for the phonetic conversions for A to Z. There's a special conversion table for spaces and for numbers. Now the code, the way it was working, it looks like it should have been loading in the address of the conversion table, but what it was loading was a pointer to the address of the conversion table. So the address of the conversion table, in fact, but it was never reversing that. It was never dereferencing that, a pointer, if you will. It was doing that for the lookup table. The lookup table, it was loading an entry from the lookup table and using that as an address, but it wasn't doing anything similar for the 0 and the space table. So that seems to be a bug to me. I removed that function. I changed the functionality so it didn't do that, and it works fine now. But I also suspect that as I said before, it was loading the D register with 0, and it was actually incrementing D and returning if that was 0, effectively limiting the search to 255 entries. And I can't help wondering, because that doesn't make any sense, because the last entry in the table should be a catch-all that would succeed for anything, and I don't understand why it's doing that limiting. So I took it out, and it seems to work fine, and I wonder if that was some kind of fix for the bug that was loading from weird random addresses, potentially. I don't know for sure. I was getting weird glitches until I found this bug and removed it. Every so often, depending on the organization of the rest of my code, I'd get weird samples playing and things, and I think it was because of that bug, it was loading completely random data. So that's a bug, but I optimized that bug out, if you will. Now, there were a few other things that I've not shown here. They weren't particularly representable, but firstly, there was a block of space in the middle of the code. The data was loaded as a binary block from disk, and there was actually a section in the middle of that binary data that was all zeros that were then loaded with the text string that was being converted. And again, that was in the type-in, which is why I don't believe this was designed to be a type-in, and I think that commercial project was first, and it was converted to a type-in. later, probably breaking the copyright of the original. But anyway, after I completely reorganized the code, replaced everything with labels, that block simply ceased to exist, and I actually use a different memory address for my strings. And that was another thing. The string is converted twice. Firstly, it's converted to uppercase and any spurious characters removed, I think, and then it's converted to phonetics, and these were two completely different memory addresses. I've changed the code, so it takes your string and it uses its temporal address and it stores the converted string, the uppercase string, and then it stores immediately afterwards the phonetic converted string, so they're both the same address and there's no wastage, whereas before there was wastage and they were two totally different places. And then the other thing is there were three routines that were doing preparation on the string. Well, first was calculating the length of the string, one was converting it to uppercase, and one was getting the last character in the last character so it knows whether there's a full stop or a question mark. I simply merged those all into the same thing. Again, they were all only used once, didn't make any sense. Okay, so that's the other changes. Now the last one we're going to discuss is a very complex change that I'm not necessarily saying you should do yourself, but it's something that I have come to enjoy, shall we say. It's also beneficial, especially if you're porting to multiple systems. What we're going to do is we're going to change a large number of compares and branches into a table, and we're almost creating a virtual machine here. I say almost because this is exactly how my 8-bit virtual machine, how its CPU processes commands. But basically what we're doing is we're creating a sequence, a program that will take a table, it will search for an entry, and then based on those successive entries, it will actually make decisions and run different subroutines accordingly. And so we're combining a large number of different functions into the same code here. Now, in a future lesson, in the next 2 lessons, we're going to discuss the actual code. So I'm not going to go into the full breakdown of the subroutines and how this has been optimized. But basically, originally, we were comparing to various characters and branching to subroutines, and those subroutines would do one of multiple things. They may have another sequence of compares, they may have a single play sample command, or they may have a sequence of play sample commands. And what I've done is I've created my routines here. And so here you've got dba, and the a there is the value we're comparing to, and then the 0 here, the 0 means execute that subroutine. So this is going to jump to the address process A. So that's the equivalent literally of this. But then some of the other ones aren't zeros. You see, this is a 255, and what that is saying is that the address sequence B is actually a set of pointers to different sound samples with speeds that should be played, and then a return should occur. So I've completely replaced a subroutine there with just 4 bytes, the B, the 255, and then the sequence B. Now in other cases, maybe we just needed to play a single sample here. So this one here just needs to play a single sample. And in those cases, what I've done is 0 is a jump to a subroutine, a 255 is a sequence, but a value of 5 here is saying play the sample specified L968F here, play that 5 times. And there would be all kinds of other versions as well. Here's an example of the sequence. 9 is saying play this sample here 9 times, this is saying play this sample 6 times, and then 0 is the end of the sequence. And you can see here part of the table scan code, but as I say, we're going to go into that in more detail next time. But this is, as I say, this is a very advanced thing once you know what you need. But this saved a lot of space because there was all of these nested branches. A compare to a value and then a jump to a subroutine like this. Well, that is 5 bytes here, and so mine here is only 4. But the point as well is, as I say, a lot of these subroutines simply don't exist in any capacity anymore, because they have been replaced entirely in the case of this this F here, where we're just playing a single sample. But these sequences as well, these are much shorter as well, because these were a sequence of calls and loads of the accumulator, all kinds of crazy stuff. Simply not as efficient. And so, as I say, creating a table of a script-like table of commands, and then creating a command processor. So you can think of that as virtual machine if you wish. I would argue that it is, but if you think that that's really just a script processor, that's fine as well, whatever you want to call it. But anyway, there we go. So the original example binary file, I believe, was 8,302 bytes. My optimized version is 6,453 bytes, a reduction of 22%. And so the point is that there's no reduction in functionality from the point of view of playing sound samples. You could do more. You could try and reduce the number of sound samples, maybe use simpler ones or lower resolution ones. I did experiment with reducing it to 2-bit or 1-bit, but the quality was so poor that it really didn't. It was really like, I can't tell what that said at all now. I'll admit it's not great at the best of times, but it was really like, well, it made some kind of noise. I couldn't tell what it was trying to say though, whereas at the moment it's actually pretty reasonable. But as I say, you could go over your code and you could try and come up with optimized versions of these, maybe that are simpler, more repetitive. You could maybe use some kind of run length encoding on the samples and things, but that was really outside of what I wanted to do for this. Unfortunately, as I said before, because I didn't write it, I can't really claim that my ownership of this and use it in my own projects, and I can't tell you you can definitely do that yourself. So any more optimization beyond this was really beyond what I wanted to do anyway. I had a lot of fun doing this. I don't usually do disassembly, and I did in this case, and when I saw all of these, in some cases, very easy wins, I couldn't resist playing with it and optimizing it. And so I think this is worth you doing. And as I say, if you do your own projects, just keep an eye out for similar things and maybe optimize them, especially if you're trying to create the fastest games or the most powerful ones using the most limited systems. Thanks for watching today, and goodbye.